Hello, and welcome back to this quiet place at the end of the day, where you can learn how the universe truly works at its smallest scale. The whole story of quantum physics from the very beginning, even while you drift off to sleep. I'm so glad you're here tonight. Maybe you met this subject once and it slipped away from you. Maybe someone told you it was too difficult or too strange and you left it there. Or maybe you're simply the kind of person who would rather fall asleep wondering what an atom is doing than lie there watching the ceiling. Whoever you are tonight, you've come to the right place. And there is nothing left for you to do now but rest. So let yourself settle. Let your breath slow and lengthen on its own. Let your shoulders come down and your body grow heavy and light at the same time, as if something had quietly loosened its hold on you, just a little, just for tonight. Nothing here will ask anything of you. My voice will stay low and even from the first word to the last, and the music will stay soft underneath it. No rise, no sudden turn, nothing that pulls you back up to the surface. It can stay with you all the way through until morning. Tonight, we're going somewhere very small, smaller than a grain of dust, smaller than a molecule, down to the scale where the ordinary rules quietly stop applying. We'll meet a reluctant physicist who found something he didn't want to find, a young man who, driven out to a treeless island by his hay fever, worked out the shape of reality there, a cat that never existed, and a question that two friends argued over, kindly, for most of their lives, without ever settling it. You don't need any mathematics tonight. You don't need to remember any of it. There's no hurry at all. If these slow journeys have become part of your evenings, a like or a quiet word below helps someone else find their way here too. And now, let's drift down, gently, into the very small. Let's begin with something calm and true. Quantum physics is not a strange corner of science. It is the ordinary physics of everything small, atoms, electrons, light. And it has never once failed a test in more than 100 years of trying. It only feels unusual because we grew up among large, slow, heavy things, and our intuition was built for those. Down at the scale of a single atom, the world behaves in a way that is perfectly consistent, perfectly reliable, and entirely unlike anything you have ever picked up with your hands. The story begins with a man who did not want to start it. In the year 1900, Max Planck was working on a very practical problem: the color of the light given off by hot objects, the glow inside a furnace. Every classical calculation gave an answer that was clearly wrong. So he tried something he considered a mathematical trick. He assumed energy could only be given off in small, fixed amounts, like coins, rather than a continuous stream. The numbers came out exactly right. He later called it an act of desperation, and spent years hoping someone would find a better explanation. The word quantum simply means an amount, a quantity, a portion, a helping. There is nothing mysterious in the name at all. Planck's insight was that at very small scales, nature seems to prefer to hand things over in whole portions rather than in a smooth flow. A little like the way you can have 2 eggs or 3 eggs, but never 2.5. What sounds like the most exotic word in physics is really just the Latin for how much. 5 years after Planck, a young clerk in a patent office in Bern took the idea seriously, in a way Planck himself had not. Albert Einstein suggested that light really does travel in small packets, not just that it is emitted that way. This explained a puzzling laboratory result, that shining certain colors of light on a metal knocks electrons loose, while other colors, no matter how bright, do nothing at all. It was this idea, and not relativity, that eventually earned him the Nobel Prize. Those packets of light are what we now call photons. A single one carries a very small amount of energy, and its color tells you how much. Red light comes in gentle packets, blue in noticeably stronger ones. On a bright afternoon, something like 100 quadrillion of them land on a single square centimeter of your skin every second, which is why light feels perfectly smooth to us. You are being rained on by something grainy, in grains far too fine to notice. The question of whether light truly arrives in packets was settled in 1923 by Arthur Compton, who bounced X-rays off electrons and measured what came back. If light were only a wave, its wavelength should not change. Instead, each scattered ray returned with a slightly longer wavelength, by exactly the amount you would calculate if one small, hard object had struck another and given up a little energy in the meeting. Light was not merely being emitted in packets, it was arriving as packets and rebounding like them. There is a number that decides how small all of this is. It is called Planck's constant, and written out in our everyday units, it is a decimal point followed by 33 zeros before you reach the first meaningful digit. That tiny number sets the scale of the entire quantum world. If it were larger, everyday objects would behave in the strange ways that atoms do. Because it is so vanishingly small, all of that peculiarity stays neatly folded away beneath the size of things we can see. By 1913, a young Danish physicist named Niels Bohr had taken this idea of fixed portions of energy and turned it toward the atom itself. He suggested that an electron cannot orbit its nucleus at any distance it likes. It has to occupy certain allowed levels, like standing on the rungs of a ladder, rather than anywhere on a ramp. To move between them, it takes in or gives out exactly one packet of light, no more and no less. It was an odd idea, and it was not fully justified at the time. It also worked beautifully. There is a question hidden in that idea that had troubled physicists for years. According to older physics, an electron circling a nucleus should continuously radiate away its energy and spiral inward within a fraction of a second. Every atom in the universe should have collapsed almost as soon as it formed. They do not, because there is a lowest rung on the ladder and nothing below it to fall to. the reason matter exists at all? The reason you exist is that the electron simply has nowhere further down to go. This is also why a flame turns orange when you drop salt into it, and why a neon sign glows the way it does. Each kind of atom has its own arrangement of rungs, so it can only absorb and release very particular colors. Spread that light out, and you get a pattern of bright lines unique to each element, a kind of fingerprint. It is how we know what the sun is made of, without ever going there. Every star quietly announces its ingredients in a language of colors. Then, in 1924, a French aristocrat named Louis de Broglie put forward a doctoral thesis with an idea so unusual that his examiners were not sure what to do with it. If light, which everyone knew was a wave, could behave like a particle, then perhaps particles like electrons could behave like waves. He even gave a formula for the wavelength. His supervisor quietly sent a copy to Einstein for an opinion. Einstein wrote back that the young man had lifted a corner of the great veil, and the degree was granted. There is an experiment that sits at the center of all of this, and it is beautifully simple. Send light at a barrier with two narrow slits in it, and on the screen behind you, get a striped pattern. Bright, dark, bright, dark. Exactly what waves do when they overlap and reinforce or cancel each other. That much was known since the early 1800s. What nobody expected was that sending something which is definitely a particle, a single electron at a time, through that very same arrangement would produce the very same stripes. Fire electrons at a barrier with two narrow slits in it, one electron at a time, so slowly that only one is ever in flight, and each arrives as a single dot on the screen behind. Perfectly particle-like, but let the dots accumulate over hours, and the same striped pattern slowly assembles itself out of them. Each electron seems to have gone through both slits and interfered with itself on the way. Richard Feynman once said this single experiment contains the only real mystery of the whole subject. In that same two-slit arrangement, put a detector at the openings so you can tell which one each electron went through, and the stripes fade away. You are left with two simple bands, exactly as you would expect from ordinary particles. Stop looking, and the stripes come back. The pattern depends on whether the information about the path exists anywhere in the world. Nature seems to offer you either the path or the pattern, never both at the same time. John Wheeler asked in 1978, what would happen if you waited? Suppose the particle has already passed the slits, and only then do you decide whether to measure which way it went. The experiment has since been done, and the answer is the same as always. The pattern depends on what you eventually measure, not on when you choose. It is tempting to describe this as changing the past, and physicists are careful not to. It seems, rather, that the question of which path simply had no answer until it was asked. This is not something that only happens to electrons. The same experiment has been done with whole atoms. with molecules of 60 carbon atoms shaped like tiny footballs, and with molecules made of thousands of atoms. Each one, sent through slowly, one at a time, builds the same soft, striped pattern. There is no known upper limit, only the growing difficulty of keeping something large undisturbed for long enough. The rule seems to be universal. It is simply very hard to catch large things behaving that way. Over Christmas of 1925, Erwin Schrödinger went away to a guest house in the Alps and came back with an equation. It describes how the wave associated with a particle changes over time, and it is still the central equation of the subject, the quantum world's equivalent of Newton's laws. It is written on chalkboards and coffee mugs and the walls of physics departments everywhere. And for a little while, not even Schrödinger himself was sure what his wave was made of. Schrödinger hoped his wave was something real and physical, the electron itself, smeared out and spread through space. It was Max Born who worked out what it actually means, and he put it in a footnote, added while the paper was in press. The wave does not tell you where the particle is. It tells you the chance of finding it in each place if you look. The square of the wave is a probability. Almost a century later, that footnote is still how we understand it. That single step is what troubled Einstein for the rest of his life. If the theory gives only probabilities, then either nature itself is genuinely undecided until it is measured, or there is something deeper underneath that we have not yet found. In a letter to Born in 1926, he wrote the line, "Everyone remembers," that the theory says much, but does not really bring us closer to the secret of the old one, and that he was convinced that he does not play dice. In June of 1925, a 23-year-old Werner Heisenberg was suffering badly from hay fever and went out to Helgoland, a small rocky island in the North Sea where almost nothing grows, and so almost nothing pollinates. Away from the flowers and unable to sleep, he worked through the night on the mathematics of the atom, using only quantities you could actually measure. At around 3 a.m, he saw that it worked, and by his own account, was too excited to sleep at all. He climbed a rock and waited for the sunrise. For a short while, there were 2 rival theories. Heisenberg's version was built from arrays of numbers, abstract and difficult, with no pictures in it at all. Schrödinger's was built from waves, and physicists found it far more comfortable to imagine. The 2 men were not especially kind about each other's work. Then it turned out, within a year, that the 2 theories were mathematically the same thing wearing different clothes. Every question one could answer, the other answered identically. They had been describing one world in 2 languages. Out of that work came the idea most people have heard of. The uncertainty principle says that certain pairs of properties cannot both be sharply defined at once. Position and momentum are the famous pair. The more precisely a particle has a location, the less definite its motion becomes, and the other way around. It is not a statement about our cleverness or our equipment, and this is the part most often misunderstood. The The principle does not say that a particle secretly has a definite position and speed while we fumble to measure them. It says that a perfectly sharp position and a perfectly sharp motion cannot both exist at once, much as a musical note played for a very short instant has no precise pitch, because there is simply not enough of it for a pitch to be defined. Some things cannot be sharpened past a certain point. One quiet consequence is that nothing in the universe is ever perfectly still. If a particle were completely at rest in a completely definite place, both quantities would be exactly known at once, and that is not allowed. So even at absolute zero, the coldest temperature there is, everything retains a small, unavoidable jitter. Physicists call it zero-point motion. The universe has a faint, permanent tremble in it, far below anything you could feel. And it can never be taken away. That gentle tremble has a visible effect you could hold in your hand. Cool almost any substance far enough, and it becomes a solid. Helium never does. At ordinary pressure, no matter how close you come to absolute zero, helium stays liquid forever, because its atoms are so light and so weakly held that their own zero-point motion keeps shaking the crystal apart before it can form. To make solid helium, you have to squeeze it. It is the only substance that behaves this way, the one liquid that never learned to freeze. Superposition is the name for a system holding more than one possibility at once. An electron can be in a state that is neither purely here nor purely there, but a combination of both, with each possibility carrying a certain weight. This is not a statement about our ignorance. The combination itself has real consequences. It is exactly what produces those stripes in the two-slit experiment. Only when the system is measured does one outcome appear, and the mathematics gives you the odds beautifully and says almost nothing about why. There is a curious effect that follows from measuring often. If you keep checking whether an unstable system has changed again and again, quickly enough, it can be held back, because each look resets it into the state you have just found it in. Physicists named it the quantum Zeno effect, after the old paradox about an arrow that never arrives. And it was shown in a laboratory around 1990 with a handful of trapped ions. A watched quantum pot really is a little slower to boil. Which brings us to the most famous cat that never existed. In 1935, Schrödinger imagined a cat in a sealed box, its fate tied to whether a single atom happened to decay. If the atom can be in a combination of decayed and not decayed, then the theory seems to say the cat must be in a combination too. And that, he thought, was clearly ridiculous. He meant it as a complaint about his colleagues' reasoning, not as a lesson. He would probably be a little dismayed to know it became the most repeated image in the whole subject. So, what actually happens when something is measured? This is the honest gap at the heart of the theory, and it has a name: the measurement problem. The equations describe smooth, predictable, entirely reasonable behavior, right up until the moment somebody looks. Then a single result appears, with probabilities that the theory predicts perfectly. What the theory does not say is what a measurement is, or why one outcome rather than another. 100 years on, physicists agree completely on the calculation, and not at all on the story. Bohr's answer was an idea he called complementarity. A quantum object has descriptions that are both necessary and mutually exclusive: wave and particle, path and pattern. You can bring out one or the other by choosing your experiment, but never both at once, and neither alone is the whole truth. He thought this so important that when he was later given a coat of arms, he chose the yin and yang symbol for it, with a Latin motto meaning opposites are complementary. Bohr also gave us a gentle rule for how the two worlds meet, and he called it the correspondence principle. As you move to larger systems, higher energies, greater numbers, the quantum description must blend smoothly into the ordinary physics we already trusted. And it does. There is no boundary anywhere, no line where one set of rules stops and another takes over. The strangeness simply fades, quietly and continuously, as things grow bigger. The set of ideas that grew up around Bohr's Institute came to be called the Copenhagen interpretation, though it was never a single tidy doctrine, and the people associated with it disagreed among themselves. Roughly, it says the mathematics tells you what you will observe, and asking what is really going on between observations is not a question physics can answer. For decades, it was simply what one was taught. It has the great advantage of working and the quiet disadvantage of asking you not to wonder. In October of 1927, 29 physicists gathered in Brussels for the 5th Solvay conference, and someone took a photograph on the steps afterward. It is probably the most remarkable group portrait in the history of science. Marie Curie sits in the front row. Einstein is in the middle, hands folded, looking directly at the camera. Bohr, Born, Heisenberg, Schrödinger, Dirac, and Pauli are all there. 17 of the 29 people in that photograph were, or would become, Nobel laureates. They had gathered to argue about what any of it meant. At the Solvay meeting of 1927, something began between Einstein and Bohr that lasted the rest of both their lives. Each morning, Einstein would arrive at breakfast with a new thought experiment designed to show that the theory could not be right. Each evening, Bohr would have found the flaw. This went on, in person and by letter, for close to 3 decades. What is lovely about it is the tone. They admired each other enormously and never fell out. Einstein once said that Bohr's mind worked like a musician's, and Bohr kept arguing with Einstein in his head long after Einstein had died. Now here is one of the gentlest consequences of the whole theory. Because a particle is described by a spread-out wave, there is always a small chance of finding it somewhere it has no right to be. On the far side of a barrier, it does not have the energy to climb over. It does not break through. It simply has some probability of already being there. Physicists call this tunneling, and it is not a rare curiosity. It is happening constantly, everywhere, including inside you. Tunneling is the reason the sun shines. For two protons to fuse together in its core, they have to overcome their mutual repulsion. And the temperature at the center of the Sun, around 15 million degrees, is simply not high enough to do it. By ordinary physics, the Sun should not burn at all. What happens instead is that occasionally a proton tunnels through the barrier rather than over it. It is rare for any given pair, and there are a great many pairs. Every warm afternoon you have ever felt arrived by way of that small improbability. The idea was worked out in 1928 by a young Russian physicist named George Gamow, who applied it to something that had been unexplained for 30 years. Certain heavy atoms occasionally emit a small fragment from their nucleus, though calculations said the fragment could never escape. Gamow showed it did not have to escape by force. It simply had to be found, now and then, on the outside. The mathematics matched the measured rates across an enormous range, from fragments that leave in an instant to ones that take billions of years. And here is something worth saying softly. When an unstable atom releases that fragment, there is no hidden countdown inside it, no wearing out, no accumulating strain. As far as anyone can tell, the moment is genuinely undetermined until it happens. An atom that has sat quietly for 1 billion years is exactly as likely to change in the next second as one that formed this morning. It does not age. It simply has, at every moment, the same small chance. That is the real meaning of a half-life. It is not the lifetime of any individual atom. No single atom has a lifetime you could look up. It is the time after which any given one has an even chance of having changed, and the time after which about half of a large group will have. This works so reliably at scale that we date bones and pottery and glaciers with it. Perfect unpredictability, one atom at a time, becoming near perfect clockwork once you have enough of them. Every electron carries a property called spin, and the name is a small historical accident. It behaves, mathematically, like rotation. It has a direction and an amount, and it responds to magnetic fields the way a spinning charge would. But the electron is not actually turning. As far as we can tell, it has no size to turn. And if you took the picture literally, its surface would have to move faster than light. Spin is simply something electrons have, the way they have mass and charge. It happens to be the thing our word for turning fits best. The experiment we now read as the first sign of spin came in 1922, and it came with a wonderfully human detail. Otto Stern and Walter Gerlach sent a beam of silver atoms through an uneven magnetic field and looked for the pattern left on a glass plate. They saw nothing at all. Then Stern leaned over the plate, and the faint silver trace slowly darkened into view. He smoked very cheap cigars, and the sulfur in the smoke had reacted with the silver and developed it like a photograph. Their poor salaries, he later said, were what made the discovery visible. That silver beam also showed something remarkable. The beam did not spread out into a smear, as a classical picture would predict. It split cleanly into two. One group deflected up, one down, nothing in the middle. Measure an electron's spin along any direction you like, and you always get one of exactly two answers. Never a third, never anything in between. Whatever spin is, it does not come in a continuous range. It comes in two, along whichever axis you happen to choose. That single fact divides everything in the universe into two families. Particles with a half amount of spin, electrons, protons, neutrons, are called fermions, and they are what matter is built from. Particles with a whole amount, photons among them, are called bosons, and they carry the forces. The two families follow opposite social rules. Bosons are happy to pile into the same state together in any number. Fermions refuse, absolutely. And that refusal is the reason the world has structure. Wolfgang Pauli wrote the rule down in 1925. No two identical fermions may occupy exactly the same quantum state at the same time. It sounds like a small bookkeeping remark, and it is the reason chemistry exists. If electrons could all crowd into the lowest level around a nucleus, every atom would be a featureless little ball, and there would be no periodic table, no bonds, no molecules, no chemistry of any kind. Instead, the electrons must stack up, filling one shell and starting the next. And everything you have ever touched follows from where those shells happen to end. Pauli was also the source of the best-loved joke in physics. He was such a formidable theorist and such a merciless critic of careless work that his colleagues claimed delicate equipment would fail simply because he had entered the building. They called it the Pauli effect and collected examples. There is a story of an apparatus in Göttingen breaking at the precise moment his train stopped at the station, on its way somewhere else entirely. Pauli, by all accounts, rather enjoyed the legend. This is where the shape of the periodic table comes from. The allowed states around a nucleus come in groups: 2, then 8, then 8 again, then 18. And those numbers are simply how many distinct arrangements the rules permit before a new level has to begin. Every row of the table ends where a group fills. That familiar chart on a classroom wall, with its odd steps and its long middle block, is not a human filing system at all. It is a picture of the allowed states of an electron. Pauli's rule is also why you are sitting on your chair, rather than sinking through it. This is not, as people often say, because atoms are little solid balls. Atoms are almost entirely empty space, and the electric repulsion is only part of the story. When you press two surfaces together, their electrons would have to enter states that are already taken, and that is not permitted. What holds you up is not really force in the ordinary sense. It is a rule about identity, pressing back. That same refusal, no two electrons in the same state, holds up entire stars. When a star like the Sun eventually runs out of fuel, it settles into a white dwarf about the size of the Earth, with the mass of a star packed inside it. Nothing is burning there anymore. What keeps it from collapsing further is simply that its electrons have run out of available states, and they will not share. A teaspoon of that material would weigh several tons. It is held together by the same refusal that keeps you from falling through your bed. Here is something else that has no everyday parallel. Two electrons are not merely similar, the way two identical coins are similar. They are the same in a deeper sense. There is no property whatsoever that distinguishes one from another, and no way, even in principle, to label them and keep track. If you swap two electrons in a room, nothing at all has changed, and the mathematics has to be written so that this is true. In the very small, there are no individuals, only how many. And now we come to the strangest and most beautiful thing in the subject. Two particles can be prepared together in such a way that neither one has a definite property of its own. Only the pair does. This is entanglement. Measure the spin of one, and you learn immediately what the other will give, no matter how far apart they have traveled since. The two are not communicating. They were never really two separate things with two separate stories. They were always one shared description. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published a short paper pointing at exactly this and saying, in effect, that it showed the theory must be incomplete. Surely, they argued, each particle carries its own real properties all along, and the theory simply fails to describe them. The paper has become one of the most cited in all of physics. And the funny thing is that Einstein was not entirely happy with it. Podolsky wrote the final text, and Einstein felt the point had been buried under the formalism. It is from that argument that the famous phrase comes. Writing to Born in 1947, Einstein said he could not believe in a theory that required what he called in German, a spooky action at a distance. He was not frightened by it. He was gently exasperated. He simply could not accept that the world would arrange itself in such a way, and he expected that some deeper, more sensible layer would eventually be found underneath. For 30 years, the question sat there, and most physicists considered it philosophy rather than physics. Bohr's reply came within months, and it is famously difficult to read. His argument, roughly, was that Einstein was assuming the two particles were separate systems with separate realities, and that this assumption is exactly what the quantum world denies. You cannot speak of the properties of one half without specifying the whole arrangement, including how you have chosen to measure. Many people at the time found the reply unsatisfying. It was only decades later that most physicists came around to thinking Bohr had the better of it. Then, in 1964, an Irish physicist named John Bell did something nobody had thought possible. He turned the argument into arithmetic. Bell showed that if each particle really does carry its own hidden properties from the start, then the results of certain measurements must obey a particular limit, a simple inequality. Quantum theory predicts that limit will be exceeded. So the question was no longer a matter of taste. It could be settled in a laboratory. He published it in the first volume of an obscure journal that folded a few years later. And it went largely unread for a decade. It took decades to build the experiments carefully enough. John Clauser did the first serious version in the early 1970s. with equipment partly scavenged from surplus. Alain Aspect closed a major loophole in 1982 by changing the measurement settings while the particles were already in flight. Anton Zeilinger and others closed the remaining gaps over the following 30 years. The answer every time was the same. The limit is exceeded, exactly as quantum theory says. The three of them shared the Nobel Prize for it in 2022, nearly 60 years after Bell wrote it down. And if you're still here, halfway along, nothing has changed, and nothing will. My voice stays exactly where it is. The music stays underneath it, and there is nothing ahead of us that rises. You can stop following whenever your body decides to. The rest of this will keep drifting quietly along beside you. There is a natural worry here, and it has a reassuring answer. If measuring one particle instantly settles the other, could you send a message that way, faster than light? You cannot. Each side, looked at alone, sees nothing but a random sequence of results, perfectly ordinary noise. The correlation only appears when the two lists are brought together and compared, and that comparison has to travel by ordinary means at ordinary speed. Nature seems to have arranged things so that the strangeness is real, and yet cannot be used to break anything. There is a small theorem from 1982 with an unexpectedly large reach. It says you cannot make a perfect copy of an unknown quantum state. Not with better equipment, not ever. Copying is simply not among the things the mathematics permits. It sounds like a limitation, and it turns out to be a gift. It is the reason a message encoded in quantum states cannot be secretly intercepted and copied along the way. Any attempt to look at it leaves a mark. You may have heard of quantum teleportation, and it is a real thing that happens in laboratories, though not the thing the name suggests. Nothing material travels. What is transferred is the exact state of one particle onto another particle somewhere else, using a shared entangled pair and an ordinary message sent by ordinary means. The original state is unavoidably destroyed in the process, which is what keeps the no copying rule intact. It has been done across a laboratory bench, across a city, and between the ground and a satellite. So why does none of this show up at breakfast? The answer that has emerged over the last few decades is called decoherence. A quantum system only shows its stripes and superpositions while it stays undisturbed. The moment it interacts with its surroundings, a stray photon, a passing air molecule, the warmth of the room, the delicate relationships between its possibilities leak out into the environment and are lost among countless particles. Nothing is destroyed. The information simply spreads until it can no longer be gathered back. Decoherence happens astonishingly fast for anything large. A single dust grain floating in a room lit only by the warm glow of its own walls loses its quantum behavior in less than a millionth of a millionth of a millionth of a second. In ordinary air, it happens far faster still. That is why a chair is never in two places, and why the two-slit experiment needs vacuum chambers and cold and darkness. The quantum world has not gone anywhere. It is simply that a large, warm object is being watched constantly by everything around it, and it settles instantly into one ordinary answer. Physicists have been steadily pushing on that boundary. In 2010, a small metal paddle, just visible to the naked eye, was cooled and placed in a superposition of vibrating and not vibrating. More recently, pairs of tiny metal drums, objects made of trillions of atoms, have been entangled with each other. Nothing anywhere has broken. It is only that keeping something this large undisturbed is extraordinarily difficult. And every year, somebody manages it with something a little bigger. Decoherence explains why we see a single world. It does not, by itself, explain why we see this particular result rather than another. And that gap is where the interpretations live. There are several, all giving identical predictions, all fully compatible with every experiment ever done. Choosing between them is not yet a matter of evidence. It is a matter of what you are willing to accept about the furniture of reality. And reasonable people have disagreed for 100 years without any bad feeling about it. One interpretation of quantum theory, proposed by a graduate student named Hugh Everett in 1957, is that nothing ever collapses at all. The equation just keeps going, and every possible outcome happens, with the observer branching along with the world. Everett's idea was received coolly, and he left physics for a career in defense analysis without ever publishing on it again. Decades later, it became one of the most discussed positions in the field. He did not live to see that. It is a quiet story of an idea arriving before anyone was ready. Another interpretation goes back to de Broglie and was revived by David Bohm in 1952. In this picture, particles are perfectly ordinary things with definite positions at all times, and they are carried along by a wave that guides them. There is no collapse and no ambiguity. The randomness is only our ignorance of where the particle started. It reproduces every prediction exactly. The price is that the guiding wave links distant parts of the world instantly, which many physicists find harder to accept than the mystery it removes. There are other interpretations still. Some propose that the wave really does collapse, spontaneously, and very rarely, so that a single particle almost never does it, while a large object does so constantly. Some hold that the quantum state is not a thing in the world, but a description of what an observer can expect. Some say properties only exist relative to other systems, with no view from nowhere at all. Each is careful, each is defensible, and none has yet been ruled out by any measurement. Meanwhile, the mathematics kept going. And in 1928, Paul Dirac found a way to make the quantum description agree with relativity. The equation he wrote is short and elegant, and it did something he had not asked of it. It insisted on solutions with negative energy, which seemed to make no sense. Dirac, rather than discarding them, spent 3 years trying to make them mean something familiar, before accepting that they must describe a new particle, identical to the electron in every way except for carrying the opposite charge. He had arrived at antimatter from a piece of algebra, without any hint from an experiment. In 1932, Carl Anderson, photographing cosmic rays in a cloud chamber, found a track that curved the wrong way. It was the positron, exactly as Dirac's equation had described. Anderson had not been looking for it and was not familiar with the prediction. Dirac himself was a famously silent man, and he held for the rest of his life that it is more important to have beauty in one's equations than to have them fit an experiment. That if the mathematics is beautiful enough, the experiments will catch up. Dirac's work grew into the way physicists now describe the very small, which is not really about particles at all. In quantum field theory, what is fundamental is a set of fields filling all of space. One for electrons, one for photons, one for each kind of particle there is. What we call a particle is a ripple, a quantum of excitation in its field, the smallest possible disturbance it can carry. This is why every electron is exactly identical to every other. They are not objects. They are the same note, played in different places. If everything is built from fields, then empty space is not empty. A field with no ripples in it still cannot be perfectly still. For the same reason, nothing else can. That would pin down too much at once. So the vacuum keeps a low background hum of its own, present in every field, everywhere, at the lowest energy the rules allow. The emptiest region you could ever prepare, with every particle removed, and the temperature at absolute zero is still humming faintly to itself. In 1948, Hendrik Casimir predicted something you could actually measure. Place two flat plates extremely close together in a vacuum, and certain wavelengths of that background hum will not fit in the gap between them, while all of them exist outside. Slightly less activity inside than out means a tiny push together. The effect was confirmed by careful experiment in 1997. And it is small, a few millionths of the weight of a grain of sand. Empty space, gently pressing two mirrors toward each other. The theory that came out of all this, quantum electrodynamics, is the most precisely tested idea in the history of science. There is a particular number describing how strongly an electron responds to a magnetic field, and it can be both calculated and measured to about 12 decimal places. The two agree. Feynman once described the accuracy as being like measuring the distance from New York to Los Angeles and getting it right to the thickness of a human hair. Whatever the theory means, it is not wrong. Richard Feynman also gave physics its most recognizable drawings. A Feynman diagram is a simple sketch of lines and squiggles, an electron here, a photon there, a point where they meet, and each one stands for a precise term in a very long calculation. He worked them out while trying to make the arithmetic manageable, and now they are on blackboards, textbooks, and conference posters everywhere. There is a van, still occasionally photographed, that he had painted with them. Add all the fields we know about, and you get the standard model. Finished in its essentials by the mid-1970s. 12 matter particles, a handful of force carriers, and a set of rules that has survived every experiment thrown at it for half a century. It is not beautiful in the way physicists hoped. It has around 19 numbers that simply have to be measured and put in by hand, with no explanation for their values. It works with almost embarrassing accuracy, and nobody knows why it is shaped the way it is. Neutrinos give superposition a wonderfully large stage. They come in 3 kinds, and each kind turns out to be a blend of 3 slightly different masses. So as a neutrino travels, the blend slowly shifts, and it can arrive as a different type from the one that set out. This was confirmed with neutrinos from the Sun and from the atmosphere, and it earned the Nobel Prize in 2015. About 100 trillion of them are passing through your body as you lie there, and essentially, none of them touch you. One piece of that model took nearly 50 years to confirm. In the 1960s, several groups independently proposed a field filling all of space that gives particles their mass. The more strongly a particle interacts with it, the heavier it is. The prediction was that this field, like all fields, should have its own ripple. In 2012, the 2 great detectors at the collider beneath the French-Swiss border found it. Peter Higgs, then in his 80s, heard the news in a lecture hall and was seen wiping his eyes. There is a phrase that comes up in all this: virtual particles, and it deserves a gentle correction. They are not tiny things flickering into existence and out again. They are a bookkeeping device, intermediate terms in a calculation, the internal lines of those diagrams, each one a step in an approximation that gets closer to the right answer, the more terms you include. Something real is certainly happening in the vacuum. The little pictures we use to compute it should not be mistaken for a photograph. Now let us come back up to the world you can touch, because all of this is sitting in your house. The transistor, the switch that every computer is built from, several billion of them in the device you may have nearby, works by controlling how electrons move through a semiconductor, and the behavior of those electrons is entirely quantum. It was demonstrated at Bell Labs just before Christmas in 1947. Every screen, every phone, every calculation anyone makes anywhere rests on that piece of physics. A laser is a quantum idea that waited more than 40 years for its moment. In 1917, Einstein worked out that a photon passing an excited atom can persuade it to release a second photon traveling in exactly the same direction, with exactly the same phase. Light coaxing more light into step with itself. The first working device came in 1960. Now that principle reads the barcodes at a supermarket, cuts steel, carries the internet along glass fibers under the oceans, and gently reshapes the cornea of an eye. The little light on your kettle is quantum physics too. In a light-emitting diode, electrons drop from one energy level to another and give up the difference as a single photon. And the size of that gap decides the color exactly. This is why LEDs come in such pure, definite shades, and why blue was so much harder to make than red. It needed a wider gap and a material nobody could grow properly until the 1990s. That difficulty was worth a Nobel Prize. There is a newer trick where the color depends only on size. A quantum dot is a speck of semiconductor a few nanometers across, small enough that the electron inside is squeezed, and the squeezing sets the spacing of its energy levels. Make the speck slightly larger, and the light it gives off shifts toward red. Slightly smaller, and it shifts toward blue. The same material throughout. The chemists who learned to grow them to order shared the Nobel Prize in 2023, and the result is probably in your television. A solar panel is the photoelectric effect earning its keep. A photon of the right energy arrives, knocks an electron into a state where it is free to move, and the panel's structure guides it in a single direction, which is a current. Below a certain energy, no amount of light helps at all. The same threshold Einstein explained in 1905. Every rooftop panel is running the experiment that first convinced physicists that light comes in packets. Even the color of gold is quantum. In a heavy atom, the innermost electrons move so fast that relativity begins to matter. And in gold, this shifts the energy levels just enough that the metal absorbs a little blue light rather than reflecting everything evenly, which is why it looks warm instead of silver. The same effect in the element next door weakens the bonds between mercury atoms so much that mercury is a liquid at room temperature. Two familiar things, both explained by how fast an electron is traveling. If you have ever had an MRI scan, you have been placed inside a quantum measurement. The protons in the water of your body have spin, and in a strong magnetic field, they take up particular orientations. A radio pulse tips them. As they settle back, they emit a faint signal, and the timing of that settling differs between tissues. the machine listens and builds a picture. It is a slow, gentle, magnetic conversation with the hydrogen in you. The second itself is defined by quantum physics. Since 1967, 1 second has meant a precise number of oscillations of the light associated with a particular transition in a cesium atom. A little over 9 billion of them. Every atom of a kind is identical, so this is the same everywhere in the universe, which makes it a far better ruler than the turning of the Earth. Every satellite navigation fix you have ever used depends on clocks like these, agreeing with each other to within a fraction of a nanosecond. Cool certain materials far enough, and something remarkable happens. Their electrical resistance does not simply become small. It goes to exactly 0. Electrons pair up in a way that only makes sense quantum mechanically and move through the material as a single collective state with nothing to scatter off. A current started in a superconducting loop will circle for years without fading. It is the closest thing we have to perpetual motion, and it is perfectly ordinary physics. Cool liquid helium below about 2 degrees above absolute 0, and it stops behaving like a liquid at all. It becomes a superfluid. It flows with no viscosity, seeps through gaps too fine for any ordinary fluid, and, most memorably, climbs the walls of its container in a film only a few atoms thick and drips off the outside of the bottom. It is not being pushed. A large number of atoms have simply fallen into the same quantum state and are behaving as one thing. In 1995, 2 teams cooled a small cloud of atoms to within a few billionths of a degree of absolute 0. And the atoms did something Einstein and Satyendra Nath Bose had predicted 70 years earlier. They stopped being separate. Their individual waves spread out, overlapped, and merged into a single, shared quantum state, a droplet of matter behaving as one object. It is sometimes called the 5th state of matter, and it exists in perhaps 100 laboratories in the world, in clouds smaller than a grain of salt. The story behind that prediction is a quiet delight. In 1924, a little-known lecturer in Dhaka named Satyendra Nath Bose sent Einstein a short paper that a journal had rejected, with a polite note asking whether he thought it had any merit. Einstein read it, saw at once that it was important, translated it into German himself, and arranged for it to be published. Then wrote a follow-up extending the idea. Their 2 names have been attached to one another ever since. There is growing evidence that biology found some of this first. When a photon is absorbed by a leaf, the energy must travel to the place where it can be used. And the efficiency of that journey is remarkably high. Some experiments suggest the energy explores several routes at once before settling on one, in the way a quantum system does. The interpretation is still debated, and the effects are delicate and warm and wet. But plants may have been doing this for a very long time. Some migrating birds may be reading the Earth's magnetic field through a quantum effect in their eyes. The proposal is that a photon creates a pair of electrons with linked spins in a protein in the retina, and the magnetic field very slightly alters how that pair evolves, changing the chemistry that follows. The field is far too weak to be felt any ordinary way. If the idea holds, a robin crossing the North Sea at night is navigating by something closer to a compass made of entanglement. Tunneling appears in your body as well. Many enzymes work by moving a proton or an electron from one place to another, and the rates are often faster than they could be if those particles had to climb over the energy barrier between. They appear to be going through it. The chemistry that keeps you warm and breathing is being helped along quietly and constantly by particles arriving somewhere they did not strictly have the energy to reach. Which brings us to computers built out of all this. An ordinary bit is either a 0 or a 1. A quantum bit, a qubit, can be prepared in a combination of both, and a group of them can be entangled so that the whole set shares a single description. This lets certain calculations explore an enormous space of possibilities in a way no ordinary machine can imitate. It is not simply a faster computer. It is a different kind of question-answering machine. It is worth being honest about where this actually stands, because it is often described as further along than it is. Qubits are extraordinarily fragile. Decoherence, the same effect that hides the quantum world from us, is constantly trying to spoil the calculation. The main effort now is error correction, spreading one reliable qubit across many physical ones. Real progress is being made, but genuinely useful machines still look some years away. It is an exciting, slow, careful field. There is one thing a large enough quantum computer would certainly do. In 1994, Peter Shor found a quantum method for finding the factors of very large numbers efficiently. And the difficulty of exactly that task is what keeps most current encryption secure. No machine yet exists that could run it at the necessary scale. Even so, cryptographers have spent the last several years designing and adopting new methods that would remain safe, well in advance of any need. The same physics offers a defense as well as a threat. Because an unknown quantum state cannot be copied, and because measuring it changes it. A key sent as a stream of single photons cannot be intercepted without leaving evidence. Two parties can therefore establish a shared secret and be confident that nobody listened. This has been done through fiber, under cities, and between a satellite and the ground, across more than 1,000 kilometers. Perhaps the quietest application is measurement. Because quantum systems are so easily disturbed, they make exquisitely sensitive detectors. Atom interferometers can feel tiny changes in gravity and have been used to map what lies beneath the ground without digging. Quantum magnetometers can detect the faint magnetic whisper of activity in a brain. The very fragility that makes these systems difficult to compute with is what makes them so good at noticing things. And here is the honest edge of the map. Quantum theory and general relativity, our description of gravity as the curvature of space and time, are each extraordinarily well tested, and they do not fit together. In almost every situation, this does not matter, because gravity is far too weak to notice at the scale of an atom. But at the center of a black hole, or in the first instance of the universe, both descriptions are needed at once, and nobody yet knows how to write down what happens. The mismatch between quantum theory and gravity has produced one gentle, decades-long puzzle. Quantum theory says information is never truly lost, while black holes appeared to swallow it entirely. Stephen Hawking argued for years that it really was lost, made a friendly wager about it, and eventually conceded. Most physicists now believe the information comes back out, subtly encoded in the faint radiation the black hole gives off. How exactly that works is still being carefully argued over in a very unhurried way. 100 years on, then, here is the situation. The theory is the most accurately tested description of nature that human beings have ever produced. It underpins chemistry, materials, electronics, medicine, and most of modern technology. And there is still no agreement about what it is telling us about the world. A physicist can use it perfectly for an entire career without ever settling that question. Very few sciences are so successful and so unresolved at the same time. Perhaps that is the loveliest part. We tend to imagine that understanding must come before use, that we work out what something is, and only then learn to build with it. Quantum physics has spent a century in the other order, flawless in every prediction, generous in every application, and still unwilling to say what it means. It works completely. It has simply never explained itself. And none of this is far away. It is in the warmth on your face when you stand in the sun, in the color of every object in this room, in the fact that the floor holds you up and the air stays air. Right now, in your hands and in the pillow under your head, more electrons than anyone could count are sitting in their allowed levels, refusing to share, keeping the shape of things while you rest. None of it needs your attention. It has been going on for 13 billion years, and it will go on all night, whether or not anyone is awake to notice. Then, in 1924, a French aristocrat named Louis de Broglie put forward a doctoral thesis with an idea so unusual that his examiners were not sure what to do with it. If light, which everyone knew was a wave, could behave like a particle, then perhaps particles like electrons could behave like waves. He even gave a formula for the wavelength. His supervisor quietly sent a copy to Einstein for an opinion. Einstein wrote back that the young man had lifted a corner of the great veil, and the degree was granted. There is an experiment that sits at the center of all of this, and it is beautifully simple. Send light at a barrier with 2 narrow slits in it, and on the screen behind you, get a striped pattern. Bright, dark, bright, dark. Exactly what waves do when they overlap and reinforce or cancel each other. That much was known since the early 1800s. What nobody expected was that sending something which is definitely a particle, a single electron at a time, through that very same arrangement would produce the very same stripes. Fire electrons at a barrier with 2 narrow slits in it, 1 electron at a time, so slowly that only one is ever in flight, and each arrives as a single dot on the screen behind. Perfectly particle-like, but let the dots accumulate over hours, and the same striped pattern slowly assembles itself out of them. Each electron seems to have gone through both slits and interfered with itself on the way. Richard Feynman once said this single experiment contains the only real mystery of the whole subject. In that same 2-slit arrangement, put a detector at the openings so you can tell which one each electron went through, and the stripes fade away. You are left with 2 simple bands, exactly as you would expect from ordinary particles. Stop looking, and the stripes come back. The pattern depends on whether the information about the path exists anywhere in the world. Nature seems to offer you either the path or the pattern, never both at the same time. John Wheeler asked in 1978, what would happen if you waited? Suppose the particle has already passed the slits, and only then do you decide whether to measure which way it went. The experiment has since been done, and the answer is the same as always. The pattern depends on what you eventually measure, not on when you choose. It is tempting to describe this as changing the past, and physicists are careful not to. It seems, rather, that the question of which path simply had no answer until it was asked. This is not something that only happens to electrons. The same experiment has been done with whole atoms, with molecules of 60 carbon atoms shaped like tiny footballs, and with molecules made of thousands of atoms. Each one, sent through slowly, one at a time, builds the same soft, striped pattern. There is no known upper limit, only the growing difficulty of keeping something large undisturbed for long enough. The rule seems to be universal. It is simply very hard to catch large things behaving that way. Over Christmas of 1925, Erwin Schrödinger went away to a guest house in the Alps and came back with an equation. It describes how the wave associated with a particle changes over time, and it is still the central equation of the subject, the quantum world's equivalent of Newton's laws. It is written on chalkboards and coffee mugs and the walls of physics departments everywhere. And for a little while, not even Schrödinger himself was sure what his wave was made of. Schrödinger hoped his wave was something real and physical, the electron itself, smeared out and spread through space. It was Max Born who worked out what it actually means, and he put it in a footnote, added while the paper was in press. The wave does not tell you where the particle is. It tells you the chance of finding it in each place if you look. The square of the wave is a probability. Almost a century later, that footnote is still how we understand it. That single step is what troubled Einstein for the rest of his life. If the theory gives only probabilities, then either nature itself is genuinely undecided until it is measured, or there is something deeper underneath that we have not yet found. In a letter to Born in 1926, he wrote the line, "Everyone remembers," that the theory says much, but does not really bring us closer to the secret of the old one, and that he was convinced that he does not play dice. In June of 1925, a 23-year-old Werner Heisenberg was suffering badly from hay fever and went out to Helgoland, a small rocky island in the North Sea where almost nothing grows, and so almost nothing pollinates. Away from the flowers and unable to sleep, he worked through the night on the mathematics of the atom, using only quantities you could actually measure. At around 3 a.m, he saw that it worked, and by his own account, was too excited to sleep at all. He climbed a rock and waited for the sunrise. For a short while, there were 2 rival theories. Heisenberg's version was built from arrays of numbers, abstract and difficult, with no pictures in it at all. Schrödinger's was built from waves, and physicists found it far more comfortable to imagine. The 2 men were not especially kind about each other's work. Then it turned out, within a year, that the 2 theories were mathematically the same thing wearing different clothes. Every question one could answer, the other answered identically. They had been describing one world in 2 languages. Out of that work came the idea most people have heard of. The uncertainty principle says that certain pairs of properties cannot both be sharply defined at once. Position and momentum are the famous pair. The more precisely a particle has a location, the less definite its motion becomes, and the other way around. It is not a statement about our cleverness or our equipment, and this is the part most often misunderstood. The principle does not say that a particle secretly has a definite position and speed while we fumble to measure them. It says that a perfectly sharp position and a perfectly sharp motion cannot both exist at once, much as a musical note played for a very short instant has no precise pitch, because there is simply not enough of it for a pitch to be defined. Some things cannot be sharpened past a certain point. One quiet consequence is that nothing in the universe is ever perfectly still. If a particle were completely at rest in a completely definite place, both quantities would be exactly known at once, and that is not allowed. So even at absolute zero, the coldest temperature there is, everything retains a small, unavoidable jitter. Physicists call it zero-point motion. The universe has a faint, permanent tremble in it, far below anything you could feel. And it can never be taken away. That gentle tremble has a visible effect you could hold in your hand. Cool almost any substance far enough, and it becomes a solid. Helium never does. At ordinary pressure, no matter how close you come to absolute zero, helium stays liquid forever, because its atoms are so light and so weakly held that their own zero-point motion keeps shaking the crystal apart before it can form. To make solid helium, you have to squeeze it. It is the only substance that behaves this way, the one liquid that never learned to freeze. Superposition is the name for a system holding more than one possibility at once. An electron can be in a state that is neither purely here nor purely there, but a combination of both, with each possibility carrying a certain weight. This is not a statement about our ignorance. The combination itself has real consequences. It is exactly what produces those stripes in the two-slit experiment. Only when the system is measured does one outcome appear, and the mathematics gives you the odds beautifully and says almost nothing about why. There is a curious effect that follows from measuring often. If you keep checking whether an unstable system has changed again and again, quickly enough, it can be held back, because each look resets it into the state you have just found it in. Physicists named it the quantum Zeno effect, after the old paradox about an arrow that never arrives. And it was shown in a laboratory around 1990 with a handful of trapped ions. A watched quantum pot really is a little slower to boil. Which brings us to the most famous cat that never existed. In 1935, Schrödinger imagined a cat in a sealed box, its fate tied to whether a single atom happened to decay. If the atom can be in a combination of decayed and not decayed, then the theory seems to say the cat must be in a combination too. And that, he thought, was clearly ridiculous. He meant it as a complaint about his colleagues' reasoning, not as a lesson. He would probably be a little dismayed to know it became the most repeated image in the whole subject. So, what actually happens when something is measured? This is the honest gap at the heart of the theory, and it has a name: the measurement problem. The equations describe smooth, predictable, entirely reasonable behavior, right up until the moment somebody looks. Then a single result appears, with probabilities that the theory predicts perfectly. What the theory does not say is what a measurement is, or why one outcome rather than another. 100 years on, physicists agree completely on the calculation, and not at all on the story. Bohr's answer was an idea he called complementarity. A quantum object has descriptions that are both necessary and mutually exclusive: wave and particle, path and pattern. You can bring out one or the other by choosing your experiment, but never both at once, and neither alone is the whole truth. He thought this so important that when he was later given a coat of arms, he chose the yin and yang symbol for it, with a Latin motto meaning opposites are complementary. Bohr also gave us a gentle rule for how the two worlds meet, and he called it the correspondence principle. If you're still here, let these last few words come slower than the ones before them. We have drifted down through packets of light and ladders of allowed rungs, past a wave that only ever offered odds, past two friends who disagreed gently for most of their lives, past particles that share a single description across any distance at all, and back up again into this ordinary warm room where you are lying now. None of it asks anything of you tonight. The sun will keep tunneling. The atoms will keep their shape. The faint hum in every empty space will carry on unnoticed, exactly as it always has. And if you drifted away long before this, somewhere among the slits, or out on that small island in the North Sea, there is nothing to catch up on. That was the whole idea. Thank you for spending this part of your night here with me on the Nightly Science Journal. Nothing ahead will interrupt you. The music stays just where it is for as long as you want it there. For now, let your breathing slow. Let all of this settle somewhere in the back of your mind, and let the rest of the way happen on its own. Sleep well, and good night.